So the next problem is stating something like this. Figure given below shows a light rod of length L rigidly attached to a small heavy block at one end and a hook at the other end. The system is released from rest with the rod in a horizontal position. There is a fixed smooth ring at a depth h below the initial position. So at a depth h below the initial position of the hook, and the hook gets into the ring as it reaches there. What should be the minimum value of h so that the block moves in a complete circle about the ring? So these are the dimensions that is given to us, and we are considering the mass is equal to m. So for this particular problem, we consider that when the system is released from here, the speed is equal to 0, and as it lowers by a height h, the block attains a value which is equal to v naught. The block will attain a value equal to v naught. So now if I consider the path which the system is defining, so it will be something like this, that this will become the fixed point or the support, and the system will be moving in this way, that this is the block of mass m, and it will start moving in this fashion in a circular path, and then over here it will reach the lowest position. So now from our result we know that when the mass is attached with a thin rod and wants to move in a vertical circular path, the minimum velocity requirement at the lowest point is equal to root over 4gl. And over here we are considering that the velocity is equal to v naught, and this is equal to length L of the rod. This is equal to length L of the rod. Now the next thing which I say over here is, as the system is falling from a height h, so the velocity v naught can be simply written as root over 2gh. Root over 2gh, if you unable to understand this, we have done simple mgh is equal to half mv square. So from here we attain v naught is equal to root over 2gh. So the system will attain the velocity which is equal to root over 2gh, and it is saying that the rod is light attached to a heavy block. So the block is having much larger mass in comparison to the length or the rod. So in this case, if I apply work energy theorem from the point over here v naught to this point, so I'll say that this is position A and this is position B. So if we equate energy from position A to position B, so energy at A is equal to energy at B. So energy at A is equal to mgl plus half m v naught square. V naught square is equal to 2gh, which is equal to, at B the energy requirement is half mv square, that is equal to 4gl. So 2 and 2 cancel out from here. If we remove all the mg's, we get L plus, all the mg's are removed, we get L plus h is equal to 2L, or we get h is equal to L. So the minimum value of h that the block moves in a complete circle is h is equal to L. So for this particular problem, h is equal to L is the correct answer that we are looking for.